S.T.A. Data was founded in 1983 by Adriano Castagnone, civil and structural engineer since 1978, and pioneer of scientific software for structural engineering. The company was born to provide civil engineering services and consulting. We have always had a particular interest in the evolving sector of IT, foreseeing the enormous opportunity of applying it in design and computation. Before focusing on software development, S.T.A. Data realized important projects both with private and state-owned companies. That's our strength, because beside IT experts, we are professional in structural design. The company is currently composed by 15 employees and several consultants, all highly professional qualified. Thanks to the continuous development of work and collaboration with the university and professional world, it is always able to offer advanced and constant updates to its customers. Application S.T.A. Data allows you to face everyday work with simplicity and effectiveness. The company goal does not end with the search of new IT solutions. The offer of S.T.A. Data includes support, training, and consulting services, including individual projects, so that the professionals are immediately operational. Thanks to the technical expertise and the state-of-the-art solution, S.T.A. Data is a solution to the real problems of designers.
Good afternoon, everybody. We at S.T.A. Data are very proud to greet you all at our third international event devoted to seismic assessment strategies for masonry structures. We are extremely grateful to all the professors and leading professionals who accepted our invitation, and in particular to Professor Andrea Penna, who has accepted once again to be our chairman. Hoping you'll enjoy this afternoon with us, I hand over to you, Andrea. Thank you all and enjoy.
Thank you, Simonetta. Thank you, all participants, all attendees, and in particular, I have to thank the distinguished lecturers that will give their presentation today. We will start with Professor Paola Santisi from the Université Côte from France. We have then a contribution by Dr. Alexandre Costa from Porto, Portugal. Then we have a contribution by Marco Tondelli and Paolo Comini of the company Seismic 360 in Italy. Then we have a contribution, say a usual contribution we had also in the past by the group of Professor Rita Bento, Instituto Superior Tecnico of Lisbon, together with Maddalena Ponte, a PhD student at the same institute, and she also co-advised by myself. And in the end, we will have a contribution by Dr. Stelios Kallioras, postdoctoral researcher at the Department of Civil Engineering and Architecture at the University of Pavia, and formerly researchers at the Joint Research Center of the European Commission in ISEP. So I think we can start with a very interesting presentation, which will be given by Professor Maria Paola Santisi Davila. The title of her presentation is Dynamic Features for the Seismic Design of Geo-sourced Masonry Buildings. It is a very interesting research project and a very interesting application of the Tremori capabilities. Please, Paola.
Thank you, Andrea. Please tell me if it's okay for the sharing or the screen sharing.
We can see your presentation now. Yeah, thank you.
Okay, thank you. Good afternoon, everybody. My name is Paola Santisi. I'm a teacher and researcher at Polytech Nice Sofia, the engineering school of the Université Côte d'Azur in the south of France. This research is developed in collaboration with Noura Zarzour, a PhD student, and Diego Mercera and Luca Lendi from CEREMA, that is a public research institution in France, and Michel Augereau, that is the head of Filiater company. The main idea of Filiater is to propose a new concept for green building construction. The idea is to use earth of the construction site and product compressed earth blocks using a machine in the construction site. So this is the aspect of blocks that are used for to construct masonry walls, and this is the photo of the first building that actually under construction in a seismic area in the south of France. So our research goal was, first of all, to select a numerical model for reinforced masonry buildings and to validate it. So we selected the 3Muri software. And the second step was to estimate the behavior factor of the building necessary for seismic design according to the Euro codes. So after these two steps that was performed, we started with the seismic design of the first compressed earth block masonry building, and now we are awaiting the end of construction to validate the model by comparison with the structural response to ambient vibration. So the idea to validate the model was to compare in terms of dynamic feature, in particular frequencies and mode shapes, using both numerical and operational model analysis. For this, we started with an existing building. It was a stone masonry building already constructed by the same company. The structure is composed of stone masonry buildings, and slab was realized with beams, joists, and plank in timber material. The building is irregular in both elevation and plan of important class 2 in a seismic area number 4 corresponding to the French mapping, and it corresponds with an acceleration in rock outcropping of 1.6 meters per second square in a ground type C. So this is the model that has been developed in 3Muri software and the related mesh, where are distinguished piers, spandrels, the rigid node between them, and beam elements. So the chaining is guaranteed by steel rod, so the box-like behavior can be guaranteed. The most difficult part in the validation of the model was the selection of the slab stiffness. So to validate the model, we selected a moderately flexible floor. I remember you that the slab is done with timber elements. It was necessary to define the slab stiffness in two directions. According to the literature, we worked in 3Muri software according with the idea that it was a new building. So the strength criteria was the ones for a new building. It meets the case of flexure and rocking, the friction in mortar bed, and the limit shear given by the diagonal crack of blocks. So here you can recognize the strength criteria in these cases selected for new constructions. Concerning the materials, the elastic parameters were obtained by tests, and the parameter we selected to calibrate by comparison with measures was the Young modulus, because it was the more uncertain parameter, considering the house is unoccupied, so the mass was quite known. We performed in collaboration with CEREMA the instrumentation of the building. So six sensors record simultaneously with only one acquisition, and in parallel one measure was done in free field far away from the building to estimate if soil structural interaction was important or not. So this ambient vibration record with operational model analysis was compared with the result of numerical model analysis. The first mode in both cases a translation, so a similar mode shape is obtained with a frequency that is calibrated, changing a little bit the Young modulus, but we obtained a value close to the test on the materials. The free Moody software gives an effective mass of almost 70%. The second mode is a translation in the other direction, so the frequency is well reproduced in both directions. As I said before, it was important to well calibrate the behavior of the slab and the connection with walls. So in the second mode, we have an effective mass of almost 30%. The third mode is a torsion. So in this case, we have a 20% of error in frequencies, but the shape of mode shape is quite similar. The effective mass is negligible in the numerical model, but is well evident in records. So here you have a summary of data obtained by free Moody and by operational model analysis. So we can observe that the error is negligible for the two translations, both in terms of frequency and in mode shape accuracy. After the validation of the model in the elastic domain, we performed the pushover analysis according with the raw code. In the case of uniform distribution, more similar to the behavior of the system in plastic condition. And the model distribution, we decided to use a different solution as the linear distribution, the unimodal distribution, only for the using a distribution proportional to the first mode displacement, and multimodal distribution in the case of a deformation obtained for a cumulative effective mass associated to the 90% of the total mass. So in this case, with this four load distribution, two direction of loading in both sides, and free option of accidental eccentricity, we have 48 simulations that are performed. Two key points of the analysis was the choice of the control point displacement. In this case, we accepted the proposal of free Moody software to use the average displacement of upper floor nodes weighted according to nodal masses. And we selected as a collapse definition the ultimate displacement achieved in a pier. So in all the analysis, the collapse is achieved in shear. Before to explain how we estimated the behavior factor, I remember some definitions. First of all, the ductility. This is the ultimate to yielding displacement ratio. The strength reduction factor is the ratio between the base shear force attained by a linear oscillator and over the shear force attained by elastic plastic oscillator for the same target displacement. The overstrength ratio is the correction if we are in the case of bilinear idealization of the capacity curve. In this case, the yielding, the force, the base shear force corresponding to the yielding, it's a bit different from the force corresponding to the first crack in a nonlinear capacity curve. And the product of these coefficients give us the behavior factor according to the raw code. So the main idea is starting with the three-dimensional model of the building. In free Moody software, we can obtain the pushover curves. And I remember you that we performed 48 simulations. And we have a similar number of capacity curves and bilinear idealization. On the other side, the raw code gives us the possibility to generate a set of accelerometers compatible with the elastic response spectrum given by the code. So the idea is to generate a set of accelerometers, impose them at the base of the 48 oscillator equivalent to the multi-degree of freedom system, and obtain the response at the top. The behavior of this oscillator is elastoplastic, so the hysteretic loop, by imposing that the yielding displacement is associated with the target displacement for a fixed behavior factor, we obtain by the hysteresis loop the ductility that is attained for the imposed load. So in this case, we obtain a curve that is associated to this specific building, that is the average ductility versus the behavior factor. I mean average ductility because it's the average for the set of accelerometers that are used. So if we have this curve, we enter with the ductility capacity of the building, and we obtain the strength reduction factor that is obtained specifically for this building. And multiplying by the overstrength ratio, we obtain the behavior factor. So just to underline some points, the bilinear idealization is performed classically by imposing the elastic strength and the equivalent area under both curves. Here you can see the 48 capacity curves that are obtained by FreeMoody software. So you can observe that the eccentricity doesn't give a difference between the curves, but you can have different strength and ductility for the different load distributions and different directions. Here you can observe the bilinear idealization of the 48 curves, and you can observe by the colors that the choice of the load distribution can change a lot of the level of strength and ductility. And here, just to verify the compatibility of the accelerometers that are used. So the set of accelerometers give an average response spectrum that is compatible with the target response spectrum of the raw code. So the 48 curves ductility versus strength behavior factor, the strength reduction factor is are shown in this figure, but we selected 8 curves that are associated to the minimum behavior factor, and we can see the numerical values with the same color in the curve. So what you can observe that these values are higher than the minimum one that is proposed by the raw code. So if we don't have an estimation for the building, we are obliged to use the minimum value given by the raw code, that is 1.5. But in this case, we have this estimation is very important from an economical point of view for the company, because it represents that if we demonstrate the ductility is higher, we can design for a lower acceleration, lower seismic loading. So this estimation is very important from an economical point of view for the construction company. So at the end, we performed the stability verification, both in terms of displacement as proposed by the raw code, and also in terms of strength. So you can see that for the uniform load distribution, the verification is positive, but for the multi-modal distribution, we have some limit values if we perform the verification in terms of strength. So it can mean that the strength verification is more restrictive. So now that we finished this theoretical part, we performed the seismic design of the building composed of compressed earth blocks. He's 40 meters long and 10 meters wide. You can see in violet the cross walls that are done with plumb concrete. The chaining is done with steel rods. The important class is 2, the same seismic area, the ground type is B. So here you can see the block is 80 centimeters long, 40 centimeter wide, and 50 centimeter thick. In the photo, you can see the elements, the cross walls and basement in plumb concrete, and the slab are done in timber. So the parameters for the materials are obtained by laboratory test, but in this case, the homogenization is performed with the formula proposed by the Eurocode. So you can see that with the strength in compression of the block of 7.5 megapascal, we arrive to average strength in compression for the masonry, that is 3.2. So this is the model that we obtained with the Frimuri and the relative mesh. The numerical model analysis gives an interesting result because as the building is very long in one direction, we have 3 mode shapes that are more or less dominant with the effective mass of almost 20%. So you observe that we don't have a dominant translational mode, but a translation of only one part of the building. So the first mode, the second one is the translation of the other part, and the third one with the effective mass of almost 20%. In the other direction, the X direction, we have a dominant translational mode associated to 80% of the total mass. So the verification is done in terms of displacement and strength. It's okay for both uniform and multimodal load distribution. In this case, in this particular case, it was important to use the multimodal distribution because the first mode, I remember it was associated to only one part. So it was complicated to give a load distribution stronger only one part of the building. So we decided to work with the model multimodal distribution, giving a more regular load distribution. So in conclusion, the stability is verified for the 12 load combination, the load distribution in terms of displacement and in terms of strength. The behavioral factor estimation is specific for the analyzed building. We are working now to increase the slab in plane stiffness to obtain a dominant translational mode shape in Y direction and to avoid this dispersion of the effective mass in several modes. As you can observe, the validation of the model has been done in elastic condition, and it would be important now to estimate to validate the ductility estimation by comparison with a shaking table test. Thank you.
Thank you, Professor Santisi. Thank you, Paola. I think that your presentation was really interesting because the project is really innovative, and in the current times when we have a lot of attention to sustainability, this project goes really in line with these which are not new needs, but there are needs that are now better understood. I don't know if there is any question from the audience. If there is any of the participants who want to ask questions, you can type in the question box. I have just one, if I'm allowed. How do you? I see that the idea is that use the soil at the site where you are building. So in principle, it is varying from site to site, from construction site to construction site. And okay, there is a process in which you work with the soil and you prepare these compressor bricks, but then you need a set of tests on the material you are getting from the site, and you have to input these the results of these tests in the model. So basically, you need a model for each of these buildings. You have to.
Yeah, thank you, Andrea. So at the moment, we work only in a first test building. So we performed the model and we have results from experimental tests for this building. But we are proposing a research project that is exactly in this with this goal, that we have, if we change the soil, we have a target performance that you want to obtain, and we need to change the receipt of the formulation each time. So our goal, if you work in a seismic zone, we need a certain level of strength, and we modify the composition of earth with water and a little percent of cement to obtain the performance that we deserve. So we have two problems in France now. One is the seismic code, the other one is the energy code, because we need that carbon balance is the lower that we are able to. So we need to select both the material and the structural features to attain these two goals.
Clear. Okay, that's really a challenging project, but very nice, interesting. Thank you again, Professor Santisi, for this really interesting and innovative presentation about your research project. I think we can, if there are no questions from the audience, we can move to the next presentation now. The presentation is by Dr. Alexandre Costa. He's one of the founding partners of NCREP, NCREP company in Porto. And he is also adjunct professor at the Instituto Superior de Engenharia do Porto in Portugal. He's a long-time user of Tremuri. He did his master here in Pavia, and since then, almost 15 years ago, he has been working in these activities. His presentation is entitled Challenges on the Seismic Assessment of the Monastery of Dinis in Odivelas in Portugal, and it looks really challenging. I hope Stefano can launch the video now. Okay.
Good afternoon, everyone. My name is Alexandre Costa, and I'm here to present you a case study regarding the Monastery of Odivelas. I'd like to thank Professor Andrea Penna for the very kind invitation to be present in this quite interesting seminar, and of course also to S.T.A for promoting these webinars around the world. Our case study, what I'm going to present you, is a case study in Odivelas, the city nearby Lisbon, where we did inspection and diagnosis and the seismic assessment. The presentation is divided in 5 different parts. First introduction, then we are going to make a small understanding around the evolution and adaptation of the monastery. Then some information regarding the structural properties, what was made, how we came out with the structural properties we used in the model, and then the main part are the challenges that we face for the seismic assessment. Last, we present some final remarks. So here is the center of Odivelas, or at least the old part where we have our case study, the monastery. I have here the back of an old church, 2 cloisters, and I have here the main square, or at least the building you enter from this part, despite this large garden here in the back. This is the other part, so the other view. You can see here the 2 cloisters, here the church, and then other buildings that were attached during years. So we have in the main part, we have 11 different constructions, and then we have another one, the 12th, is an isolated building. And if you take a look to this, you have here the church, the 2 cloisters. We are speaking about 10,000 square meters of implantation area. And then we have 2 to 3 stories, which means that in the end, we have around 20,000 square meters of total construction area. Some start information is from the 13th century, possibly the construction date is from the 1295. It took 10 years to be made with several adaptations and damages along the years, and one of the most important was the 1755 Lisbon earthquake. That in the end, just some parts of the church and also of the cloisters remaining until nowadays from the original construction. It should be also mentioned that during the 20th century, several modifications were made, resorting mainly to reinforced concrete slabs and also some beams. Here's some historical information. You can see, for example, some mill buildings that were built around the mid of the 20th century. Here in the facade, also new openings. These 2 buildings. Then, for example, the gym that is building number 9 in the middle of the 20th century with 4 main columns to support the roof, and then some supports to the balconies where now we have reinforcing concrete slabs and the metallic roof. And the church, where we can see the original part of the church and what was damaged and what was reconstructed, and also some loss of quite interesting paintings and decorated ceilings that were lost during the years. Here we have building number 6, that is, let's say, mainly one of the most important or most interesting, with decorated tiles on the walls and decorated ceilings, supported on the timber structure. And here the 2 cloisters, where we have stone columns supporting supposedly vaults, but these vaults, they have reinforced concrete slabs. As you can see here in cloister, it is part of number 10, and then in part 11, the same thing. Here, everything is made of reinforced concrete, and here you have a timber structure. What is going to be done in the monastery? The municipality has the objective to turn out the monastery back to the local community, because nowadays it is not used. So the main point is going to be used as a museum in some part of the church, and so this is a historical part somehow, including this part also. Then have the municipal services in other parts, and here an auditorium, here residences for students, and here a music hall. So it's going to be a very interesting intervention, but with this occupancy, it means that we are working with building or constructions that can be considered as the importance class type 3 according to Euro Code 8. Regarding structural properties, 121 survey windows were made for timber, reinforced concrete, and masonry characterization. Timber were defined, the properties were defined based on the species identification analysis, mainly pinus. Then reinforced concrete, several core samples were made, as well as rebound Schmitter tests, and regarding masonry, several wall surveys were made with by archaeologists because this is a national monument. It's not possible to put, or at least to define, three main families for stone masonry, and also two types of brick masonry, one on solid bricks and another one with two horizontal holes. In addition to that, we did some flat checks. So this means that making use of all this information, the material definition was made, making use of the Italian code. Then the challenges started. The first one was regarding the seismic action. And why is that? Because being an importance class 3 building, we need to do the seismic assessment for 3 damage levels, for damage limitation, for severe damage, and for near collapse. And in our national annex, when we're working with existing constructions, we can use what is called the reduction coefficients for existing constructions. And they are here in this part. However, while for severe damage and damage limitation, they decrease the seismic action, for near collapse, the seismic action is increased. Let's look to type 1. Let's say that for severe damage, we are using just 75% of the seismic action that is considered for new buildings. But if we are doing the seismic assessment for near collapse, we are increasing the seismic demand by 62%. On the other hand, when we are working on the assessment part, so not on the retrofit, we can even reduce 90% of this action. So this means that, for example, for type 1, for severe damage, we have the seismic hazard, or at least the PGA that comes from the seismic hazard. Then you have 90%, then you have 75%, but then we multiply it by the coefficient of importance. This means that in the end, we have almost the same seismic action that is considered for new buildings with importance class of 2. So this is somehow discussable. On the other hand, if you are looking to near collapse, if you do the same calculations, we are increasing more than twice the seismic action. So this means that while here we may not be a lot conservative, here probably we are going too further and we are being too severe for the building. Regarding modeling, we have two approaches. The first one was what our main, or the first choice was to be made. It was individual models, so we could control better the behavior, understand better the buildings, and we could simulate different story heights. Also, you can refine or do better local calibration, making use of operational model analysis results. So it could make isolated buildings. But the problem is that as they are all interconnected, the interaction with adjacent constructions is not easy to do it. And then we have another approach that was to do a global model with interaction that is already implicit in a model with the geometry, but then we have the difficulties to evaluate the individual behavior of each building because we are looking to a global capacity curve. Moreover, using Tremuri, we couldn't, or at least to have a numerical model that was easier to control and to understand. You need to use an uniform story height because the levels, they are more or less the same, but they have some differences, but they are not the same, but they are not so different. So this means that this could influence somehow. So one of the points was to use an uniform story height for all the buildings, but then also do a sensitivity analysis for different, 3 different story heights. We started from the individual models, but since the beginning, we decided not to go in this direction. For example, for building number 4, a simple model, this wall here is this wall. So if you do a seismic analysis in this direction, is the damage pattern, and you can see that damage concentration is here in this wall. Even the model configuration, you have just translation, so you are not connecting this building to that building. So this means that the problems probably they are not going to be this in this wall. We try also to model with some local supports, also in starting looking or modeling the remaining walls, but then we start losing the perception of the model and how the building was behave under seismic action. And the same thing came out to building number 6, that is this one. So we have here 2 perpendicular walls, and you cannot simulate this easily and control the behavior. So we start adding walls. For example, here, starting adding this wall, there, here, there, but then everything started to be connected. So in the end, we decided to go to this challenge that was to build a global model. Global model, it was somehow a challenge, but it was possible to do it. It was very nice to see that Tremor is also capable of making these large models. And then the analysis was made looking to the global models, but look individually for each building. We try also to model, or at least to adjust somehow the local properties of each building, making use of the operational model analysis results. And some example what came out is that, for example, while in this direction, Y direction, for example, this is the damage pattern for a specific point of the capacity curve, you can see that you have more or less the damage distributed along several different buildings. So you have not a damage concentrated in one of the buildings, while, for example, on the analysis to the right, you can see that, for example, in this direction, you have the damage, or at least the failures, mainly concentrated in this part, in building number 2. So this means that despite working with a global model and the global behavior, we could, or at least we're looking to the individual behavior of each building, and from there assess what was the problem and what should be tackled in the strengthening design. Then we have the problem of the out of plan. So we use also Tremori to do it, and local mechanisms were defined based on the literature and also on the local connections that we assess on site, and also take into account the existing cracking patterns, and as well as the presence, for example, of tie rods. Moreover, we wanted also to evaluate the influence of connections between horizontal and vertical structure, so the importance of slabs and roofs, and it was also to evaluate with these simulations that it has a strong influence even for seismic demand. So this means that we need to then, on the strengthening phase, to really connect horizontal to vertical elements. So we came out with 24 local mechanisms for all the monastery. For example, here a typical gable failure, and here, for example, a simple overturning or an overturning, take into account the connection at the roof and at the floor level. This was made for different buildings, for different parts, and just to show just some 2 examples. For example, a global overturning here for building number 4, that is the building that we show in the beginning. If we connect to the top, we can increase even to 10 times seismic capacity. The same thing to other walls. So this means that on the strengthening phase of the monastery, this should be one of the key points to be used on the design. So just final remarks. So it was a real challenge of the case study, mainly to the dimension and the different wall typology, etc. And it was also important with a proper model to simulate interaction between the buildings. In order to do that, of course, you need to do some modeling simplifications, but it's very important so we can control in the end the model and understand what is going on. And we could, from the global capacity curve, take a look to local analysis. And definitely it can be said that Tremuri expedited the process of modeling and analyzing results within a reasonable time frame. Let's say that all this process took between inspection diagnosis, material characterization, ambient vibration tests, and seismic analysis took more or less 3 months. So I hope you enjoyed this presentation, and definitely if you have any question regarding presentation on this topic or any other, just send me an email by this email address. And of course, we have the contact of Ana Simões, that is a representative in Portugal, and you can also always rely on S.T.A. Thank you very much for this opportunity, for this time. I hope you enjoyed, and I wish you the very, very nice webinar with these very interesting speakers. Thank you.
So I had the opportunity to thank in advance Dr. Alexandre Costa for this interesting and challenging also work on this modeling of such a complex structures. I think we can also ask him to join next year to show the complete outcome of these analysis on these very complex buildings, and maybe some of the participants can ask him their question now or prepare for next year's seminar. I would then go for the next speaker. The next presentation will be given by Paolo Comini of Sismica 360. Paolo Comini and Marco Tondelli are presenting this interesting talk, which is not completely far from this kind of application that we had in this challenging and complex irregular structure, because they are presenting a presentation of a title, Use of Single Wall Analysis in the Seismic Assessment of Flexible Diaphragm Buildings, which is commonly the case in monumental and complex historic structures. So I leave the floor to Paolo Comini and ask him to stay in time, but provide an interesting presentation as we all expect.
Okay. Thank you, Andrea. Just a question: can you see my screen full?
Yes,
full
yes,
screen?
you can see. I think if I can say a couple of words about Sismica 360, which is a company established in Italy a few years ago, but active actually worldwide, and in particular in several European countries. And I don't know if your presentation will be about Italian or non-Italian structures.
Non-Italian.
We will see. We will see. Okay, non-Italian, but okay.
Okay, thank you, Andrea. Good afternoon. My name is Paolo Comini. I am a structural engineer and I work for the company Sismica 360. Today I will talk to you about the use of wall analysis in the assessment of buildings with flexible floors. So firstly, I will quickly introduce who is and what does the company I work for. Sismica 360 is a consulting company active in the field of seismic engineering. We assist both engineers and engineering firms in the seismic and structural analysis of the new and existing buildings. We have been involved in various projects in residential, public, and also industrial sectors, both in Italy and abroad, as Andrea mentioned before. And this includes a major campaign to assess the seismic vulnerability of residential buildings in the Groningen region in the Netherlands. in which we participated together with our Dutch partner, eConstruct. From 2018, we have analyzed about, just one moment, about 300 buildings in the Groningen region. And this campaign will serve as the background for my presentation today, which is based on our daily based professional activity. The issue of earthquakes in the Groningen region is linked to the gas extraction. The gas field was discovered in 1959 and is the largest in the Western Europe in terms of size. The problem is that 90% of the buildings in the region are built with masonry and were not designed to withstand seismic forces. So for this reason, since 2014, alongside the reduction in gas extraction, a campaign was assessed the seismic vulnerability of buildings in the region has been started in order to identify any critical issues and reinforcing buildings where necessary. The seismic vulnerability assessment is carried out carried out in accordance with the guidelines NPR. These guidelines have undergone several modifications and updates over the years, leading to significant differences in the definition of the seismic capacity of buildings. These guidelines are available in Tremuri among the list of national codes that can be applied in the calculation. The NPR guidelines differ quite significantly from the codes we are accustomed to, such as, for example, the Eurocode 8. In the bottom box of the slide, you can see some peculiar characteristic aspect of this guideline. The newer NPR guidelines push the structural capacity much further than, for example, Eurocode 8, as you can see from these values. We have talked about the capacity. Now let's discuss about the demand. The seismic input is obtained from what is called NPR web tool, which is essentially an internet accessible database. By entering the geographical coordinates or the address of the building, it provides the elastic spectrum and also other data that can be useful in structural analysis. Due to the progressive reduction in gas extraction, the seismic inputs has significantly decreased over the years, which has had a major impact on defining the demand. At the beginning of the assessment campaign, so in 2018, for example, most buildings required rather major retrofits. In particular, diaphragms were being retrofitted by stiffening them in any case. And so for this reason, there was no emphasis on analyzing them with their real flexibility. With the various updates of both the guidelines and the seismic input, the trend changed and the need arose to analyze building using the real stiffness of the floor diaphragms. So single wall analysis became very important. Also in this case, in the bottom of the slide, I present some information regarding the Dutch case. So the return period, the PGA, the maximum PGA. The buildings that my colleagues and I have come across over the years mainly fall into three typologies. So detached houses, terrace houses, and barn houses. Regarding walls type, Dutch buildings have much thinner walls compared to those we are accustomed in seismic countries, like, for example, Italy. The majority of the structural walls have a thickness of around 100 millimeters and are primarily made of two materials, so the clay and the calcium silicate. The use of the calcium silicate began around the 1960s. Thicker single wall of 210 millimeters are typical for perimeter walls in buildings from the early 1900s, while newer buildings have cavity walls on the perimeter. Let's focus now on the floor diaphragms. We can have three major structural typologies. So the first one is timber floors, timber diaphragms, constructed with either a simple boarding, so simple blacking, or one or two panels of OSB, oriented strand boards. These three solutions have increasing stiffness. The second structural typologies are hollow core slabs, which can be of two types. The first one is a very typical Dutch typical components that are the Neobo slabs, which are hollow core slabs made with perforated brick units connected with the cement mortar. These were commonly used in construction from the 50s to early 80s, and usually they cannot be considered as rigid. The second typology of hollow core slabs are the press-stressed hollow core slabs. These are typically in construction from the 80s onwards and often have a collaborating topping sufficient to be considered as rigid. Lastly, we have the cast-in-place reinforced concrete slabs that can be considered as infinitely rigid. The diaphragms play a crucial role in the seismic response of buildings, and two limit conditions can be considered. So the first one is the limit condition of infinitely rigid diaphragms. These are rigid diaphragms in their plane that do not experience shear deformation. When dealing with such a diaphragm, so for example a reinforced concrete slab, a cast in situ reinforced concrete slab, global analysis are the most appropriate. The second limit condition are the infinitely flexible diaphragms. These diaphragms have a significant distortion in their plane, and they are unable to transfer horizontal forces between parallel and transverse walls. So in this condition, each wall responds individually, and the most representative analysis is or are the single wall analysis. Between these two limit conditions, there are the intermediate all the intermediate cases. Let's consider this very simple building consisting of two walls for each direction. The mass can be concentrated at the top of each wall. Therefore, for a specific direction, we have the stiffnesses of the two walls and the stiffness of the diaphragm. When I say stiffness, I also mean strength, as in nonlinear analysis, such as in a pushover analysis. The two are interconnected because in the nonlinear range, initial stiffness is no longer a good parameter. If the stiffness of the diaphragm, so the green one, is much lower than that of the walls, especially the more flexible one, so the red one, K-flex, in that case, each wall is responsible for the mass concentrated at its top. Therefore, in this case, the most representative analysis type is the single wall analysis. On the other hand, if the diaphragm is much stiffer than the walls, in that case, global analysis can be used because the diaphragm can couple the behavior of the two walls and torsional effects are also possible. In reality, actual buildings lie somewhere between these two scenarios. Our approach is to consider the ratio between the magnitude of the stiffnesses involved. So if the diaphragm, so the green one, has a stiffness in the same order of magnitude as that of the walls, that is, if the K diaphragm is at least 10% of the stiffness of the weakest wall, so the red one. In this case, we perform global analysis. In the other one, single wall. So now the problem is how to evaluate the stiffnesses. Regarding the stiffness of the diaphragms, the NPR guidelines provide tabulated values of second stiffness for different types of floor systems at various drift levels. Specifically, they provide values at two drift levels, 0.1% and 1%. Not all types of floor system are included in the tables. So for those not listed, reference can be made to specific scientific literature. The biggest issue is how to evaluate the flexibility or the stiffness of the walls. One might think of considering the elastic stiffness of the wall piers, which, however, is not representative of the nonlinear behavior of the masonry, and at the same time turns out to be a very high stiffness that almost always forces a single wall analysis in the case of timber floors or semi-rigid floors. Therefore, we devised a more, how to say, non-linear or practical approach. And I want to underline that what I show you is our approach. I underline the word our. It is not proposed in any official document. It is not. It is just a formulation we came up with to give us a rule in applying one type of analysis or the other. So, step one, since building a 3D model of the structure is required for conducting a single wall analysis in Tremori, we propose using this model to perform a global pushover analysis with rigid diaphragms. Step two, the shear force at the base of the most flexible wall is evaluated at a specific displacement delta, which I will define shortly. Step three, the stiffness is calculated as the force divided by displacement delta. And finally, step four, this stiffness is compared to the diaphragm stiffness. Oh, sorry, I don't know why. The displacement delta we have chosen in the displacement for the displacement, which correspond to a 0.1% in plane shear drift for the diaphragm floor. We have selected this default value because it often falls within the nonlinear range that is typically around 4 to 6 millimeters, while still being far from the ultimate condition. Now I present you a very simple case study, a building located in the city of Uskert, or village of Uskert, in the northern part of the Groningen region. It consists of a ground floor and a first floor, located under a gable roof. Regarding the ground floor, all the walls are made of clay brick masonry, except for the wall indicated in green, which is made of timber. The floor separating the ground floor from the first floor is made of timber and consists of timber beams arranged in the y direction with a spacing of around 1 meter, topped with timber planks. This type of diaphragm can be considered quite flexible. So we apply our procedure. So step one, firstly, we perform a global analysis with a rigid diaphragm intramural. Here are the results. Everything is verified, green color. Now, let's consider the walls arranged in the X direction, so the direction perpendicular to the floor joists. We divide the floor into two diaphragm fields, diaphragm 1, the blue one, and diaphragm 2, the red one. We have to consider their dimension in order to calculate the displacement relative to the drift of the 0.1%, for which we are going to evaluate the shear force at the base in each wall. The relative displacement for a drift of 0.1% in the two diaphragm fields are, for diaphragm 1, approximately 5.5 millimeters. For diaphragm 2, approximately 2.25 millimeters. Now, let's refer to an analysis in the X direction, such as, for example, the pushover number 3 in the negative direction without eccentricity. At this point, for each wall, we can query the results from Tremori and extract the shear values of each element of the wall in the X direction at the target displacement that we have calculated. In this slide, I present an example for the wall P1. This wall is connected only to the diaphragm field number 1. So the displacement at which we evaluate the shear is 5.45 millimeters. So the closest pushover analysis step to the target displacement for wall P1 is at a displacement of 5.48 millimeter. We can extract the tabulated values of all the elements belonging to that wall, and the total base shear for the wall, for this wall P1, will be the sum of the shear values at the base of these elements. We follow the same procedure for all the three walls in the X direction and that we are analyzing, and the results obtained are shown in this slide. We can see that the wall P1, P2, and P3 have base shear values approximately equal to 28 kilonewton, 66 kilonewton, and 48 kilonewton, respectively. By knowing the base shear and the associated displacement at which the base shear was calculated or evaluated, we can now compute the stiffness of all the three walls, denoted as KP1, 2, and 3. It can be observed that the wall P1 is the most flexible. We evaluate now the stiffness of diaphragm using the approach proposed by Brignon et al., which depends on the three contributions, so flexural contribution of the planks, the shear one, and the slip lane contribution of the nails. Now, knowing the stiffnesses of the walls and the diaphragm, we can compare them and see if the diaphragm stiffnesses are in the same order of magnitude as the wall stiffnesses. As you can see, the ratio between the two stiffnesses is always less than 10%. Therefore, we can conclude that the diaphragm stiffness or the diaphragm stiffnesses are not in the same order of magnitude as the wall stiffnesses. So according to our, and underline our, practical approach, we should perform single wall analysis. Out of pure curiosity, I performed two analyses, one for each direction on the global model, but this time I included the actual stiffness of the floors to observe the behavior. As you can see, the shear deformation of the diaphragm is significantly pronounced, and in the X direction, the global analysis transforms into a pseudo single wall analysis, more or less, with no meaningful outcome. At this point, we will use the single wall analysis tool provided by Tremori, so we can compare the results. In this slide, I show you the comparison between the global analysis performed on a model with rigid diaphragms, the yellow one, and the single wall analysis. As you can see, all the global analyses were verified, as indicated by the green color. However, the single wall analysis for the wall P5 resulted in a red color, indicating that it did not meet the verification. They did not meet the verification criteria. Similarly, in this slide, I have provided a comparison between the global analysis conducted on the model with flexible floors and the single wall analysis. And once again, all the global analyses were verified as indicated by the green color. These are the results, the critical pushover for the wall P5, and we can see that the ultimate displacement is reached at a drift of 1.3%, which is higher than the value prescribed by the Eurocode, which is equal to 1.06%. In conclusion, diaphragm stiffness is a key parameter in assessing the seismic behavior of buildings. And for this reason, it is important to evaluate it as best as possible. Through the procedure presented today, we have established a criterion for determining when to employ a global or single wall analysis. By comparing the in-plane stiffnesses of masonry walls and diaphragms, we can make informed decisions about the appropriate analysis approach. The Tremori software allows the user to define the in-plane stiffness of a diaphragm, and in case the diaphragm is not sufficiently rigid, also allows the user to perform single wall analysis. Finally, it is important to note that performing global analysis on structure with highly flexible diaphragms may yield misleading results, as I showed before. Therefore, it is crucial to consider the relative stiffnesses of the components involved to ensure accurate and representative analysis outcomes. So, thank you to everyone, and for additional information, you can find here my contacts and also the email address of the company and the website of Seismic 360. Thank you.
Thank you, Paolo. Really an interesting presentation with a topic which can be not that easy to handle in practice, because you know, unless you establish a criterion, and you have done exactly this to decide what is a flexible diaphragm, what is not, and how to deal with in these cases, then in many practical cases you tend to follow one or the other solution based on expert judgment, or say simplest procedure that you may find. I don't know if there is any question from the audience to you. Otherwise, I can just maybe ask you to, not really to answer a question, but to repeat something that you have already specified. I mean, you have set your procedure, your criterion to decide when using one or the other, and how can you be, let's say, sure that this assumption, this criterion works, or how can you test? I mean,
Yes, usually when usually we apply our criterion, but at the same time usually we check this with the global pushover analysis. So we perform also a global pushover analysis with the real stiffness of the floor, and we check if there is the possibility to perform a real global analysis with the with the real stiffness of the floor or not. There are some cases where it's very difficult to understand if we have to perform one or the other. So we decide to follow our criterion in order to assess this particular case. But in the majority of the case, since the thickness of the walls of the Dutch buildings is very low, because it's around 100 millimeters, we are more or less sure that if there is a timber floor with only planks, we are 90% sure that the single wall analysis are the best options. Instead, the problem is when, for example, we have different structural typology. So, for example, only one OSB panel, a floor with only one OSB panel, or with these particular Neobo floors, and also in that case we developed a different approach in order, because they are very particular, very strange structural typologies, are similar to the SAP floor, the Italian SAP floor floors, but yes, in general, when you have simple planks, we are more or less sure that for Dutch buildings we have to perform a single wall analysis. Instead, in the other cases, it's more difficult to understand which is the best solution. So we use our approach in order to assess before the assessment which analysis we have to perform.
Thank you. It's really clear and useful. I mean, this kind of approach, because there are cases in which you say it's simple to say, okay, this is rigid enough, or this is surely very, very flexible. But there are a number of intermediate cases, so in which you are not sure about the relative stiffness of the elements and the contribution of the different elements and the different fields of floors and different stories. So this is really an interesting and say a topic that suggests that some research, some solution that have been found may be very helpful for many users. Thanks again for your very nice presentation. Okay. There is a question for Paolo.
Yes.
Yeah.
Where can I see the question?
No, this is probably I guess for Professor Santisi, because I found these in which have you run models with soil that has had additives added, like some fibers? I think that this is for the first presentation.
Okay.
I don't know if okay, we can maybe move to the next presentation, and then if Professor Santisi is still online, can reply to this question. So the next speech will be by Maddalena Ponte. She can hear us.
Hello.
Okay. Hello, Maddalena. Maddalena, together with Professor Rita Bento, is going to present this interesting presentation about modeling Timber-Masonry-Steel building with using the equivalent frame method. So we are stretching the equivalent method, equivalent frame method to perform this modeling and analysis of a mixed structure with masonry, but also timber and steel components. So please, Madalena, we are all curious.
Exactly. Thank you. Thank you for the introduction. Can you see my my presentation? I'm sharing it.
Yes, we can see.
Okay. This work was carried out in Lisbon in Instituto Superior Tecnico, coordinated by Professor Rita Bento with a large team of architects and civil engineers. It's about a timber masonry steel building using the equivalent frame method, as Professor Penna said. And I'm going to start explaining our motivation, the case study, which is named the APPI building, the experimental dynamic characterization, then the equivalent frame modeling, the numerical results, and conclusions. So the motivation started with the complaints of vibrations felt by the users of the Association for the Protection of the Early Childhood, which is APPI, the owner of this building. This building is their museum, and on one side is their museum, and then on the other side is their offices. So they felt a lot of discomfort in the offices and in the museum due to the level of vibrations. You can see the building is very near the river in an area named Santa Apollonia in Lisbon, and a discomfort level was assessment was carried out, and now I'm going to present you is the seismic assessment that came after. The building was constructed in 1901 in Santa Apollonia, and it was designed by one famous Portuguese architect, Ventura Terra. It is a building representative of the national construction of the epoch for its style and construction techniques, which makes it part of the building of the country's built cultural heritage. The case study, which I will call always APPI to be easier, it's an almost rectangular asymmetrical in plan. It's 10 by 22 meters squared, with walls of more or less 4.85 meter height. To obtain the geometry and the correct characterization of the building, a laser scan was carried out. Also due to the importance of the building, which is a museum, so like this we have everything registered. The ordered point cloud was created with the laser scanner, and then a model in BIM was developed by a student, which allowed to create then the numerical model. You can see here we are entering in the BIM model. We can see that the building is one floor on this side, and then on the other side we have 2 floors. It is a mezzanine, and here we are passing from the point cloud to the beam, and this is the part of the offices. So the part with the 2 floors. The building structure was renovated in 2014. It had to be completely rebuilt, since it was found out that the majority part of the structure was all very damaged. So the renovation kept the same exterior layout as the original. So they substituted the elements, but they kept the layout with the timber frames and the masonry walls. But then I added an alteration to the architect's design. They added a mezzanine type steel structure on the inside, as you can see here on the right side of the plan. This is the part of the offices, as we saw in this video. And then on the left side, we have just 1 story height, which is the museum part. I also show to you the 6 timber frames, because this building, in fact, is a timber building, which the main structure that carries the loads are the timber frame elements. In this, actually, this drawing is from NCREP, the company of Alexandre Costa, who just presented before. So they did the evaluation of the state of the timber elements before the renovation. And so you can see here that the building was the first part to be built in the renovation was the timber frame. So the timber frame is what carries the vertical loads. The foundations were also rebuilt. The old ones were destroyed. They built new foundations, and then the timber structure. The rooftop is also with OSB flakes, and then they started adding the masonry as an infill. So the masonry used was the same type of bricks that were before, so vertically perforated clay bricks with 12.2 centimeters thickness, and the layout was kept the same, as you can see here. Now talking about the steel part, the mezzanine. The mezzanine had independent foundations to the outside part of the structure, but then it is connected, as you can see here on the image in the detail on the right side. You can see here the connection of the mezzanine to the timber frame. So it's connected to the timber, the 6 main timber frames. The ambient vibration tests were carried out to characterize the structure, and the positions that we used to obtain the main vibration modes were the 4 points on the corners of the building. We used triaxial accelerometers with a full range of -+1 G and sample frequency of 200 Hz. The results for the first vibration modes for each direction are here presented. So in the transverse direction, we call the Y direction, it's 4 Hertz more or less, and then in the X direction, which is the longitudinal one, more or less 5.05 Hertz. The building, the numerical model was built in Tramuri, of course, and this is the 3D model, as you can see. The timber elements considered are the structural maritime pine, which is the most typical type of timber to use in Lisbon. Class C18EE, so structural. These properties and this class were all retrieved from the Portuguese standards that I mentioned here. These were the values used. Then for the steel elements, we used the S275. Everything was very detailed for the steel part in the renovation works. These were the sections we used. And then the material, the masonry elements. For the masonry elements, we considered vertically perforated clay bricks with lime mortar. The values were obtained from the Italian standard, and we used also the more Coulomb laws, and with shear drift and bending drift also defined in the codes, with a confidence factor of 1.2. Then this is a very important part, the modifications of the automatic mesh. It was so the building has very particularities, as it's not a masonry building, it's a timber building with masonry parts. So some part we had to adapt to represent the real case. The first thing that I want to mention is that this part of the timber frame, you can see here this triangle. So in order to represent it, we define these horizontal elements as flexurally rigid elements with a very high inertia and plastic modulus. And then also the vertical elements that frame the window and the doors, they were not explicitly modeled. As you can see here in these images, we noted that some of them, they are not connected to the foundations, and others, you can see on the second image, they were patched. So the old part of the element, the old timber element is still here, and then a new element was patched. So these elements, the ones around the windows and the doors, they just served for it to frame the windows and the doors. But then the 6 main timber frames, as you can see here, they were modeled as they were the structural parts and were in fact new elements connected to the foundation, as you can also see here, detail of the connection. Also, modifications to the automatic mesh had to be carried out manually in order to represent our real case. So, as I said, the timber elements around the doors and the windows, they were not specifically modeled, but they were taken into account as they in fact altered the dimensions of the piers of the masonry piers. So in here, this low part, you can see below the window, I had to alter the size of the rigid notes to consider the horizontal timber beam that exists here and that separates the different masonry. So that part had to be carried out and manually introduced in all the model. Then, as the building has the mezzanine at the middle height inside, only on one side of the plan, and on the other side it's just one floor. When you add the floor, Tremuri divides the entire plan with this level, and we don't want that, so we also changed this mesh, as you can see here on the left side, and also on the transverse wall, as you can see here, an entire pier was created. So the intermediate nodes on this side were all eliminated, but then on the right side, where in fact there is the mezzanine, we keep these nodes, so we keep this level, and the piers and also the timber columns, they are divided as the mezzanine will have an influence here, creating damage in this part. Furthermore, also there is this alteration here in the connection of the pier to the rest of the structure. So it had to be created an extra nodes in plans in order to guarantee that the masonry element was not connected to the timber column, because as it was observed in the details and in the photos of the renovation, we can conclude that the timber frame was built initially, then the masonry part was added, which means that the masonry in fact doesn't carry almost any significant load, basically just its self-weight. So in this case, we create a separate nodes, and we connect these two elements with this horizontal element, which is a timber beam. As it's in reality, there is a timber beam around the top of the building, and like this, we guarantee that almost no loads from the roof are transferred here to these piers. About the loads, so again, to guarantee that the masonry walls do not carry significant vertical load besides their self-weight, instead of defining a mass to the roof elements here, we didn't define the mass of the roof elements, but we applied by concentrated loads where the roof will in fact be supported. So these concentrated nodes here. All of these aspects that I just detailed were essential to calibrate the model. Some of them we actually understood not immediately in the beginning when we started to model, but then when we started to calibrate it, we understood that, okay, the structure was built this way, so we have to make these alterations to take into account. All of these steps were very important. And like this, we could obtain a good calibration with errors of 10% to the experimental results. And we also obtain a similar deformed shapes. You can see here the first row is the frequency in the transversal direction, in the y direction. In the case of Tremuri, we can obtain some curvature in the deformed shape of the longitudinal walls, which in the experimental results we cannot see as we only used the 4 sensors in the corners. And then the x direction, again very similar to the experimental deformed shape. You can also see here the deformed shape of the walls, the masonry walls with the timber frames, and also the metallic steel elements. About the numerical results, pushover analyses were carried out for the longitudinal x direction and the transverse y direction of the building using uniform and triangular loads distribution. You can see here that the triangular is the most demanding one, so that will be the one that I will detail the most. Here, looking at the horizontal direction for the triangular loads distribution, I marked the 3 points of this curve as the definition of the ultimate displacement was also an important step of this work. So the Tremuri continues the pushover curve indefinitely, as there is no limit, drift limit defined for the beam elements. So therefore the beam elements continue to resist in this building, the timber frames, the timber pillars. The first point, the blue one, is when all the masonry piers reach the ultimate displacement. So when the masonry is collapsed, you can see here for the column, for the colors, all of them reach collapse. This would be the most conservative ultimate displacement, ultimate point. Then we can go with the curve. You see there it still has strength, and you can go until more points. The second point that I marked here is the plasticization. The plasticization of the steel beams. So you can see here, in this case, the beams on the mezzanine, on the floor, they are plasticized. And then we continue to increase the strength of the building and reach to the point where in the main facade, all the timber pillars are plasticized. So this was our limit. We could even exploit maybe even more, but this will depend on the level of knowledge that we have on the connections of the timber piers, the timber columns to the foundation. So if they are well connected, the rotation that this connection allows or not. And we don't have that information, so we stopped here at this point. Again, for the y direction, we can observe the same points. The blue point where the masonry piers reach the ultimate displacement, then the plasticization of the steel beams, and in this case also the columns. For this direction, the steel structure suffers more plasticization, and then in more elements, and then the plasticization of all the timber pillars on the transverse facades as the last point in the curve. So just to conclude, my presentation is almost finishing, and I would just like to say that it's important to know the construction sequence and details of the structure in order to create a realistic model. This was the one of the very important aspects while building the model and making sure that it was representing the real structure. As you can see, the details that I showed, the first sequence starting with timber frames, then masonry, the connections of the steel structure to the timber frame. And then, even though Tremuri is specialized in masonry structures, we can see from this work that it has the capability to model the mixed timber masonry buildings. There are limitations in the modeling, of course, of the timber steel frame buildings. We see that it's necessary to add the possibility to define the drift limits to the timber elements in Tremuri. It is also necessary, we didn't carry it out here, to make the evaluation of the connections between the timber elements and the steel elements also. It is also, while modeling this type of buildings, it might be necessary to manually alter the macro element mesh to better capture the real behavior of the structure, as I showed here with these examples. And last, the ultimate point of the pushover curve can be defined considering different limit states. For instance, a code-defined drift limit to consider that as the ultimate displacement of the curve. The failure of the masonry piers, as we showed here, a more conservative approach, or then the plasticization of the timber piers. And last, a full development of the plastic mechanism, but only if there is the confidence in the connection of the pillars to the foundation and if the rotation capacity is known. Thank you very much. My presentation is over.
Thank you, Maddalena. A really nice, interesting presentation, and in particular, I think what has been really, say, impressive is the advanced use of the capabilities of the software that you have managed to adapt to a complex and new application. This is really an interesting and I think a very informative presentation, also showing say non-standard application and proper use of what the program allows to. So the use of some reasoning on the model and on the loads to be applied, the type of connections, the subdivision of elements, and all this stuff. I think it is really helpful also for other users to see what can be done. Let's say forcing a little bit the standard modeling into what we need in this specific case. I don't know if there is any in the audience who wants to ask anything, because I think what could be also one say possible outcome of this presentation is that somebody tries to adapt this modeling strategy to a different topic, to a different let's say system, where we have, let's say, mixed, let's say, frame elements and equivalent frame elements, let's say, in combination. The issue of modeling mixed structure is not resolved. I mean, it is something that's still open to new inclusion, new additions, and one of the critical issues is particularly the way of, let's say, we can manage to force loads to go to the elements that are built before, and they have started, say, carrying loads before the other were built in. So in a way where we all know there are several uncertainties, but at least we can let's say adapt and force the model to follow what are our, let's say, thinking and reasoning on the model. So if there are no other questions from the audience, I would just congratulate with
Thank you.
Penna
Thank you for the invitation.
Rita. So we can go to the last presentation. Now we can give the floor to Dr. Stelianos Kallioras, if Stelios is here. Okay, Stelios is there. So Dr. Kallioras is ready, and he's presenting a very interesting case. The case Dr. Stelianos is presenting starts from a real building, a real stone masonry building in Greece, in which, thanks to the analysis, we managed to let's say to redirect the strengthening path on this building. I give the floor to Stelios for this presentation. Stelios, just to let you know, we are watching the presenter visualization instead of the.
Yeah. Let me see what I can do.
Because you have probably a second screen, so you should.
Exactly. Maybe I should just disconnect one screen.
You can do that, or you can share the right one.
I'm old school, so I disconnect one screen.
Simple.
Okay.
Okay.
Now you see?
Yes, we see. Okay, please go on.
Good afternoon to everyone. I would like, first of all, to thank Professor Penna for his kind invitation to attend and participate in this webinar, which is very informative. One can really see what Tremuri can do in both research and practice-oriented projects. My presentation falls into the second category. I brought today a case study from Greece, say fast seismic assessment of an existing stone masonry building, and say this was a project we undertook a few months ago by a very good friend who bought a new property in Greece, this very beautiful stone masonry building, which was constructed in 1967 and was later extended in 1990. It was originally a stone masonry, a two-story stone masonry building that was later extended. And a reinforced concrete frame was added on the side of the building. The structure is located in Petalidi, a village in the Messenia region of Greece. That region is quite seismic prone. Seismic hazard is pretty high. So the new owner of the structure was interested in knowing whether the structure is habitable, and if no, what is a fast and effective and low-cost way to strengthen the building and render it habitable in a reasonable amount of time. And to carry out this study, we used the commercial version of the Tremuri software. We developed a 3D equivalent frame model. The challenge was to it was a mixed structure, so we had to take into consideration the existence of the reinforced concrete frame that was attached to the stone masonry building. Probably the two structures interact. Back at the beginning of the study, we didn't have much information about construction details. Later, the client provided us more details, and we managed to this way to refine our model. After building an equivalent frame model, we perform some model analysis to see what is what are the tendencies of the building in response. There is some fundamental vibration modes, and we perform global pushover analysis to see what are the pathologies of the building and or to compare the different retrofit strategies that we proposed based on how they contribute into improving the lateral load resistance and displacement capacity of the structure. We refer to different light strengthening interventions, such as stiffening the existing floor diaphragms that were flexible, improving the quality of the masonry through repointing joints, and at the end we also examine an hypothetical situation of applying textile reinforced mortars on the external side of the walls. The client provides us with lots of information, so documentation dating to 1960s, a lot of photographs from which we could deduct info about the local and construction details of the building, and very well detailed architectural drawings. Here you can see some photos of the building. The building seems being in a pretty poor condition. I forgot to mention it had a basement that was no more than 1.5 meters deep. In our analysis, we disregarded the existence of the basement. The client had already decided to introduce a reinforced concrete slab at the ground level. So here you see the two street facades of the stone masonry structure. On the front side, there is a reinforced concrete addition. It's a balcony. We consider it necessary to model it as the slab adds extra weight to the masonry walls, and therefore it significantly affected the analysis results. We also introduced reinforced concrete elements to simulate the reinforced concrete frame. These are simple beam elements. The level of detail, of course, varied in the course of the study. At the beginning, I modeled the two buildings not attached. Later, based on the information provided by the client, we figured out that the two structures are well attached. So the beams of the reinforced concrete frame are well embedded into the very thick stone masonry walls, which are 50 centimeters thick. Here you see the floor diaphragms of the stone masonry portion. They are in a pretty bad situation, very thin and sparsely spaced timber girders support a very thin and corrupted timber sheathing. The floors are supported only in the longitudinal building direction. Let's say that the longitudinal building direction is I don't know if you see my mouse, the one on my left hand, not the one where the balcony is, but the other one. Here you see details of the rigid diaphragms, providing floors in the reinforced concrete frame structure and the balcony. You're already familiar with the equivalent frame modeling strategy. The automatic mesh option of the Tremor software didn't have any particular problem into discretizing the structure into piers, spandrels, exit nodes. The geometry of the building was pretty regular. Membrane elements were used for the simulation of the flexible and rigid floor diaphragms. As I already mentioned, we had plenty of information regarding the geometric and mechanical characteristics of the materials, as the client had already performed a series of in situ visual inspections and non-destructive tests to determine the compressive strength of concrete and the stone measuring. Also, information regarding the steel reinforcement was pretty clear, and there was no uncertainty. And actually, going through the documentation, we realized that the reinforced concrete frame was a pretty well-designed frame. We performed some model analysis to see that disregarding connection between the frame and the stone measuring building, we could get something like a vibration mode that you see on the left, where it would have been very unrealistic. We consider later connection between the reinforced concrete frame and the stone measuring building to see that the two structures collaborate well. The fundamental period in the X building direction was 0.2 seconds. Due to the flexible floor diaphragm present in the stone measuring structure, we could identify single wall modes and in plane floor distortion. Same thing also in the Y building direction. We perform a pushover analysis in the original building configuration. We adopted the uniform and modal load pattern. We're controlling always displacement, the average displacement of the second floor of the flexible floor of the stone measure building. As you see, the analysis was not verified in the X direction. That could be because that was presumably because of the fact that the flexible floor diaphragm didn't provide enough didn't transfer sufficient gravity loads to the walls, and didn't provide sufficient coupling between orthogonal walls. So as you see here, while in the building appears quite weaker in the in the Y building direction, which is the one along the balcony, which is the span direction of the floor, due to simply the fact that there are no gravity loads resulting from the floors. So based on this evidence, the first thing we proposed was the stiffening of the floor diaphragms and the addition of extra weight through the addition of RC topping. We propose also different ways our client could move into applying this retrofit solution. The first step would be the strengthening of the perimeter of the new floor diaphragm through a reinforced ring beam that reinforces also the connection of the diaphragm with the perimeter stone masonry walls. We assumed 15 centimeter thick reinforced concrete topping. We also provided detailed drawings on the application steps the client should follow, and how with small details like this he could assure a good coupling between the old timber seating and the new reinforced concrete slab. We performed push-over analysis on the retrofitted building to see that the response was significantly improved. In particular, here you see that after stiffening the floor diaphragm, we do not have single modes anymore. The building behaves in a box with box exhibits a box type response where parallel walls move together. Here you can see the improvement of our strengthening proposal on the lateral load capacity and displacement capacity of the structure. And now the structure was verified, the strength structure was verified. We went one step further to examine what would be the extra benefit of applying textile reinforced mortar jackets on some or all of the stone masonry walls, to find out that although in some cases that would result in increased lateral load resistance and increased stiffness. For the cost of this retrofit intervention, maybe the benefit wouldn't be that effective. So this is my presentation. I would like to thank you for your attention. It was a simple case study showing how, in a very fast way, I built a numerical model of a mixed structure and performed a very fast assessment of the structure before and after strengthening.
Thank you, Stelios. I think that, okay, thank you also for keeping the time not too long. Your presentation, I think, is an excellent conclusion for the webinar today, because basically you have shown how even in a simple case like this, or relatively simple, we can support the design of retrofit interventions by proper modeling, by proper simulation, and this is very helpful for practitioners and also for yes, for conceiving suitable retrofit strategies that, in principle, we think they are correct, they are helpful in enhancing the properties of the building. But then when you want to quantify, you need tools that are flexible enough to adapt to the real building constraints and the interaction of different parts that, of course, we know, and possibly we know better after the intervention. But in any case, thank you for your presentation. I think that we are now at the end of this very interesting webinar. I really thank you, Stelios, and all participants. I would ask all participants to switch on their cameras. And I don't know if there is just Stelios or, okay, thank you, Maddalena. And thank you, Paolo. And thank you, Rita. Possibly Professor Santisi had to go because she asked to be in the first part of the webinar for this reason. So I thank you all for joining. Sorry, you just disappeared in my screen. Okay, I thank you all. I thank you all the attendees for staying for to the end of this very interesting set of presentations. I hope some of them will follow up next year, so we will see the results, possibly the implementation of the retrofit interventions, the completion of the analysis, and possibly some interventions in the monastery, which is shown by Alexandre Costa, and maybe we will also have new interesting cases of buildings, complex buildings, irregular buildings, and I don't know in 1 year what will happen. Certainly, many of us will be together at the World Conference in Earthquake Engineering, which will be held in Milan, and S.T.A also will be there. So I thank you all again, and I say you goodbye to the next webinar. Bye-bye.
Thank you.
Bye-bye, thank you.
Thank you all.
Bye, thank you.